Hello and welcome to Pascal's Principle. I thought I'd put together a nice little video to kind of review what we did in class. And so I've got the definition of Pascal's Principle up here. It is that the pressure exerted at one surface of our fluid is equal to the pressure at any other surface. And so if you remember the equation from class, that is P1 equals P2. And what this shows is that pressure at spot number 1, which could be anywhere on the fluid, is going to be equal to pressure at spot 2, which would be anywhere else. And so this is nice, showing kind of changes. If we increase the pressure at one spot, it would increase at all the spots. And that's what is useful about these hydraulic lifts. We have a small area over here where we put our input force in, what we would actually push down on, and that force is going to get magnified over a large area. The reason why it gets magnified is because if we increase the pressure here, the pressure across the entire fluid is going to increase, and the pressure equation is pressure equals force over area. And so if we have an increase in pressure and the piston over here is very large, that's a pretty large area, we'd have to have a big number on top to end up equaling to that pressure. So there's more room essentially for the atoms and molecules of the fluid to contact with this piston over here, and that's essentially why we're able to lift large forces like these pickup trucks. A couple useful applications. You can kind of test this out yourself if you're interested. This is a water bottle, and as long as you have it full of water, you can test out Pascal's principle. All you need to do is squeeze on it and then feel the different parts of the bottle. So each of these arrows kind of represents the force exerted on that area of the bottle. And notice how they're all equal in size and equal distribution as well. Once we squeeze on it, they don't just get bigger where your hand is squeezing, it gets an increase in pressure across the entire thing. And so if you're squeezing here, feel with your other hand up here what the pressure feels like, or feel what it feels like down here. It should be exactly the same throughout. Another useful application is for air mattresses, right? An air mattress is essentially a giant bag filled with air that you sleep on, and it lets you sleep on kind of bumpy, rough ground if you're camping or something like that, because even though there might be bumpy things beneath you, they really don't affect your sleep at all, because while this rock here that's pushing into the air mattress would increase the pressure, it's exerting a force on the air mattress, it doesn't translate to this specific spot on your back. It's going to equally distribute the whole way across the air mattress, and so you get a nice flat surface to sleep on. Probably the most important part of the video is doing a practice problem, right? So I've got one written over here. Anytime you do a practice problem, I really recommend doing a drawing of the pistons. And so our pistons look kind of like this, right? A small piston, and then we've got our large piston. And the reason why you should draw this is to help keep it sorted out, right? You want F1 with A1, and you want F2 with A2. Probably the most common mistake that we see is people that put F2 over A1, or they get them kind of confused around. So make sure you do the drawing. It takes a little bit of extra time, but it will kind of ensure that you don't put things with the wrong spot. So I got my two areas here, right? 2 centimeters squared and 4 centimeters squared. The larger of those two, 4 centimeters squared, is going to be my large piston, right? So I'll put it over here next to the large. And then the small one, of course, is 2 centimeters squared. The load on the large piston is 3,200, all right? So the problem has told me that 3,200 goes with the large piston, and that's where I'll put it. What is the input force that must be applied to the small piston? So there's our unknown. We don't know what the force is to the small piston. Now, I'm about to click my button here, and as soon as I advance it, the drawing is going to disappear. So if you'd like to save the drawing or make one on your page, push pause and do that now. I'm going to go ahead and plug the numbers into the equation, and we get something like this, right? F1, that's what we're solving for, over 2 centimeters squared equals 3,200 newtons divided by 4 centimeters squared. There's two different ways you can attack this. I really recommend using the cross multiplication method, where we would multiply our F times 4 centimeters squared and our 2 centimeters squared by 3,200 newtons. What this does is it gets the numbers out of the denominator. They're not really useful for us down there, so let's pull them out of the denominator, get everything on top where we can work with it all at once. Here's the result of my cross multiplication. Again, F1 is what I'm solving for here. Before I try to move anything around, which we will do eventually, I'm just going to simplify this side. Both of these are numbers. 3200 and 2 are numbers, and so I'm multiplying them. I can do that right now, and I will. Notice how my units didn't change. These don't cancel out when you multiply. In fact, they just multiply together. So my unit here is 6,400 newtons times centimeters squared. I will be getting rid of some of this in a little bit. Back to the other side, I still have F1 times 4 centimeters squared. I don't really need this 4 centimeters squared over here. I'm trying to get F1 by itself. So we're going to move over this 4 centimeters squared to the other side of our equality. The best way to do that, because we're multiplying here, is to do the opposite. The opposite of multiplication would be division, of course. So we divide. And if we divide each side by 4 centimeters squared, we haven't changed the equality. I'm doing the same thing to each side. Each side remains equal to itself. When I divide by 4 centimeters squared, however, I will cancel some things out on the left. I'm also going to cancel something out on the right. And this is what it looks like. Right? 4 divided by 4 is equal to 1. So it cancels. Centimeters squared divided by centimeters squared, well, anything divided by itself is also going to be equal to 1, so it cancels. And then, again, centimeters squared, those will cancel out to 1. And we don't really need to write these times 1s in there, because anything times 1 is itself. So they cancel out really nicely, and I'm left with just my unknown variable and this fraction over here. We're going to simplify the fraction. So we would type 6,400 divided by 4 in the calculator, and the calculator would tell us that that is equal to 1,600 newtons for F1. I like that this is less than my large piston. Remember, my large piston was 3,200 newtons, so we've got a number that's less. The force is smaller, and we're talking about the small piston, so I like that force. I do not like the sig fig, so we have one more step. Remember, if we're multiplying or dividing, which we did both in this problem, we can only have as many sig figs as the least. We only have one sig fig. We only have one sig fig. 3,200 has 2 sig figs, but it's as many as the least, so we need to round this to 1 sig fig. So I would look at the 1 as my sig fig I'm keeping. The 6 tells me to round it up, and so my final answer is 2,000 newtons. And so that's my video to review Pascal's principle. I hope that it helped. Please feel free to rewind, fast forward, anything you'd like to help you review this problem, this type of problem. We'll see a lot of these on tests and quizzes coming up. Please see me if you have any extra questions or would like to review.